So yeah, I want to talk about persistent homology and the categorical language that is used in certain parts of it. So traditionally, in data analysis, there has been so we are going to start with a motivating construction, which is that in data analysis there has been a big part of it that consists on regression, which models correlations in data, and then classification techniques like clustering, which gives us information about the partitions of the data. Then there are also some techniques for dimensionality reduction, like manifold learning, which give an information about the underlying geometry of the data points. So persistent homology is a technique in topological data analysis to obtain information about the topological features of the data. And it consists, so when we have like individual data points, it consists of firstly constructing a simplicial complex from it and then applying homology to it, persistent homology. And we're going to explain these two steps now. So how can we calculate homology from a simplicial complex? So I'm going to describe it basically. So we're going to start with, for example, describing what zero simplex is, what n simplices are. So zero simplex is like a point. One simplex is a line connecting 2 points. Two simplex is like that, like a filled triangle. This is two simplex. And a simplicial complex is gluing these together. So we can form what are called P chains, which are sums of simplices. So P chain, we can see it's a like formal sum of simplices sigma. So this is P simplices, and these are coefficients which are usually in a field. So we say in a field, and we usually take this field to be Z2. So this is either 0 or 1. So these P chains form a group together with this formal sum, and which is called the group of P chains. CP, and it is usually CP of that, where this is the simplicial complex. And then, for example, given a simplex, P simplex, we can obtain the faces of the simplex, which in this case are, for example, these 3 lines. And the sum of these 3 faces is what is called a border. So the border of, so this is 2 simplex, we call this 2 simplex sigma, for example. The border of sigma is actually a 1 chain, given this definition. So given that we define the group of P chains like this, we can see that the border is actually an operation, a group homomorphism actually, that goes from the group of P chains to the group of P minus 1 chains. And inside this group of P chains, there is actually 2 important subgroups, which are P cycles and P borders. So intuitively, P cycles are chains whose border is 0. So notated as this. And P borders are the ones that are actually, so it's P borders are P chains who are borders of another, in this case, P+1 chain. And relating this back to this group homomorphism, the P cycles are actually the kernel of this operation, and the P border is the image of the border operator. Well, we should probably say this P+1, but it's not necessary. And from these two subgroups, if we quotient this out, we get what is called the homology, the P homology of a simplicial complex, which is the quotient of P cycles by P borders. And the main takeaway here is that, oh, sorry, I didn't see the chat. Yeah, so yeah, exactly. So the formal sum is exactly so this group of P chains are the elements of the P chains, and concatenating, so to say, or putting together this P simplices by this formal sum is what it gives the group structure. And the main takeaway here is that homology describes the holes. What I mean by this is that for a given P, so the zero homology of a simplex encode the connected components, the one homology are like one-dimensional holes. The two homology are the two-dimensional cavities, so to say, just two-dimensional holes also. And in general, for example, if you have a simplex, for example, like this, we can see that the one homology, so the one homology is different because there's a hole in the middle. For example, if you got a simplified complex with three different connected components, then the zeroth homology has dimension 3. And in general, for example, a tetrahedron has a two homology.
I guess I might not be the only one that's forgotten what group quotients are.
Yeah. So group quotient, yes. So group quotients are, in this case, we can think of equating or collapsing everything in the denominator. So we'll say that, so the homology are the P cycles where all its P borders are identified with each other. So that's why, for example, if we got a simplicial complex like this, we know that here this is one cycle, and this is actually also a P border. So that's why this describes a homology. In this case, in case that this were filled, then this is no longer a P border. And that's why the homology in this case, the one homology is 0 because there's no hole anymore.
The other way around, if it is filled, then it's a border, right?
Yeah, exactly. Yeah. So it's a two border. So it's a border of this of this middle thing. When quotient by the p borders, we discard everything that is a border of a higher simplex. So in this case, so if we have, for example, two disconnected components, these two vertices are not faces of a one simplex, because there's no one simplex connecting these two. Therefore, these are two distinct connected components, and that's why the zero homology in this case has dimension 2. In case these were connected because of the quotient thing, these two vertices are going to be faces of this one simplex, and that's why when quotienting this is only, so the p border connects these two, and therefore when we had two distinct connected components, now we have only one. And this is, of course, so general for any dimension p. But the first, so 0 homology, 1 homology, 2 homology is what is more intuitive for us. So we know how to, we get an intuition of how we get the homology out of a simplicial complex. But remember that the initial data that we had in the beginning was just a point cloud, just a set of points in a space, for example, in a Euclidean space or in a metric space or whatever. So how can we construct simplicial complex from it is the question now. And there are not only one method, there's many, but for example, I'm going to describe now what is called the Vietoris-Rips complex, which takes a given radius r, and then for each point, it looks at the points, at other points which are inside this radius. And then for a given radius, it constructs a simplex out of them. So for example, if you go to this radius, in this case, this point has this and this one as simplexes. Therefore, in the Vietoris-Rips complex, for a very small radius, we can see that that all the points are isolated, so everything is disconnected. But when we get a big enough radius, for example, this one, a big enough radius, we start connecting these different points. And then we can construct a simplicial complex, which has indeed a hole in the middle. So the homology becomes, the one homology becomes of dimension 1. But the problem is that if we increase the radius too much, then we start connecting the points across too. So the hole disappears and the homology becomes 0 again. So the question now is like, which radius should we choose for a given data set to really see the homology that it has? And persistent homology proposes just, well, why not look at all of them? So the idea is the following. So we have a radius which goes in this axis, and we construct the Vietoris-Rips complex for this parameter r, which we vary across not just a single radius, but many. So for very low values of r, we still get a lot of disconnected components. Then we start seeing some some holes and some higher dimensional simplices and so on. And at the end, we get again that the simplex is connected. So every vertex is connected with any other. We can see then down below here that the homology of this Viatoris Rips filtration, so the filtration, what I call filtration now is like a complex with varying radius. The homology of it also changes across radius. So for example, the connected components for dimension, the homology of the zero homology, we can see that for a very low value of R has a lot of different connected components. But as we increase the radius R, the Viatoris Rips complex starts merging these together. Therefore, there are fewer connected components that survive. And at the end, for example, there's just one component, which in this case is just all the vertices connected with each other. In the case of one homology, we can see that again there are some holes here, for example, that appear for varying radiuses, and we can see that these topological features are again persisting across the radius. That's where the name persistent homology comes from. So there's a specific point where which is called the birth index or the birth radius and the death radius for a specific topological feature. And what topological data analysis does is to look at this kind of diagram and see, for example, that if we got here a two-dimensional two homology, so in this case like a two-dimensional cavity, we can see how significant it is. So for example, if you got a feature that begins here and ends up to here, then this one hole is actually a inherent property of the data and not just, for example, random noise, for example, like this little hole or this little hole. And all this is represented in this kind of diagram, which is called a barcode. So a barcode represents the different components of homology, of persistent homology. So we have seen these two steps, and in general we have like a pipeline that is followed always. So we start again with data in a metric space, or just data points in Euclidean space, for example. Then we apply the Viatoris Rips construction to get a filter complex. So in this case, so if we start, for example, with these 4 points, then we get a filtration that is like these 4 points, and then what we saw before. So this here. And then we apply the K homology to obtain this persistent module. And the barcode is the thing that represents this persistent module. So where does category theory come in all this? We can start defining a category of simplicial complexes. So these are, for example, here we have a complex K, which consists of this zero simplex and then this complex. So these are all objects of this category. And what are morphisms in the category of simplicial complexes? Well, these are simplicial maps. That is a mapping of vertices which respect the simplicial structure. That means that every simplex here is mapped onto a simplex there. So this is a category, and then homology can be seen as a functor. So the simplicial K homology, in this case over a field Z2, that is meaning that an edge is either there or not, is a functor that goes from these categories of simplicial complexes to the category of vector spaces. And again, this is given by the quotient that we saw before. So in this case, if we have this, so this is like an object, a morphism, and an object in the category of simplicial complexes. This is mapped. For example, in the case of the one homology, this is mapped to the vector space with one dimension, because there's a hole here, and this is mapped to the zero dimensional vector space, because here we can, so here there's no hole. In this whole complex, there's no hole, so it's zero dimensional. If we look, for example, at the zero homology, so this is connected components again, we can see that in this simplicial complex there's two connected components, this triangle and this whole vertex, and this is mapped by the simplicial map to this one simplex and this zero simplex. So this is two connected components mapped to two connected components. And in the category of vector spaces, the morphisms are linear maps, which in this case indicate like which one goes to which. So it doesn't lose the information of the simplicial map sending which vertices to which, or which complexes to which. For example, this could have been again 0, 1, 1, 0, for example, if we had like this. Then again, the Vietoris-Rips complex can also be seen as a functor, and indeed it can be also seen as a bifunctor if we allow the radius also to be a parameter. So if we fix a given radius, then it's just a functor that goes from the point cloud to the category of simplicial complexes. This can be seen as from the category of metric spaces which are enriched over this category. So this category is just a category of a pre-order, which describes the distances. So in the category of metric spaces, if we have, for example, two elements, the morphism. No, sorry. So if we have there's a description of distance embedded into the enrichment of this category of metric spaces. The morphism in this category are short maps. That is, maps that reduce all distances between points. So then this Vietoris-Rips complex is a bifunctor because it sends for a given radius and a given metric space or a given point cloud. It generates a Vietoris-Rips complex of this radius. Then if we got a morphism in this category, that is a radius which is smaller than another one, then we have got also a morphism between simplicial complexes. So that's like an embedding of one complex into another. There's a simplicial map from one to other. But moreover, if we've got a morphism in the category of metric spaces, that is a short map. So if we got, for example, so this metric space only consisting of 4 points. So this is X. And then this smaller one mapping, so each point, each point to these. So this goes to here, this goes to here, this goes to here. Then there's also an embedding of the resultant via Rips complexes, because the radius needed to make a simplicial complex here by the short map is also reduced here. So therefore, if we have a simplicial complex arising with a given radius, here, then for sure it is here, because of the short map, everything is contracted. And then we come to the main point, which is persistent modules, which, if you remember, they are like vector spaces connected with each other by linear maps. And we can see that these are actually diagrams in the category of vector spaces, which is indexed by pre-order of n elements. So this is just like the category of, it's not the discrete category of an object, but it's connected, it's skeletal, connected to with from 1 to 2 to 2 to 3 and so on up to n. So a persistent module is actually a functor that goes from the category n to the category of vector spaces, and it can also be seen like an object of this functor category. So maybe it's also like notated like this. It's the same. Then there are also like many possible generalization of this concept. For example, relaxing the indexing category to natural numbers, to integers, to even reals, which gets a bit tricky when trying to decompose these things. And also, if we have the homology, we said that we calculated the homology over Z2, which is a finite field. So the homology of a complex in Z2. But if in general, we can calculate it over a ring. So for example, Z, and this then has no longer a vector space structure. So this we can only get abelian groups, or in general abelian categories. And there's also, for example, generalizations that they don't index vector spaces, but morphism between vector spaces. So this 1, 2, 3 gets mapped to these. And these are collateral modules and so on, but it's not important right now. Zigzag modules, for example, are modules which don't have all the same orientations. They can have linear maps going in different directions. But in general, our main example of persistent modules are going to be vector spaces indexed by natural numbers or by a finite subset. So now that we got persistent modules, we can think of how we can decompose these things into like smaller building blocks or like simpler things. We recall that persistent modules are functors. And in the case of zigzag modules, which I briefly introduced before, these are also functors that go from quivers to the category vector spaces. So a quiver is just like a directed graph. And zigzag modules are functors that go from the free category of the graph, that is looking at the vertices of the quiver as objects, and the maps between them as morphisms. So this is the free category, and so we allow also compositions. So for example, if we had another one, we can also, this is allowed. And we can see that zigzag modules are functors so that go from f of q to vec. So this is a representation of the quiver. And what this allows us is to use a result of quiver theory, which tells us which quivers are decomposable. This is called Gabriel's theorem. And it turns out decomposable quivers are only of this type. We are interested in the first one because these are like persistent modules, regular persistent modules, but there's also like other kinds of quivers. So what this tells us is that there's a unique decomposition of this of a persistent module, and by decomposition, what I'm trying to say is that if I, for example, a persistent module does go from, I don't know, V1 to 3, this is actually a direct sum of V1 prime going to 0, for example, and then V1 going to V2 prime going to 0, things like this. So we can calculate starting from the persistent module, that is, so defining the vector spaces and the linear maps between them, we can decompose this in a unique way into these simpler building blocks. So these are intervals. These are called intervals because like they start at a point and then they last up to a point. And this gives like an algorithm to calculate it. And we can, because of this is why we can describe the homology in this decomposed way. That is, these intervals are actually this decomposition. That is, the persistent module, for example, this persistent module can represent what is the homology of the Viatori-Rips complex with radius 1, with radius 2, and with radius 3, for example. And then this decomposition tells us that there is a topological feature that begins at 1 and dies at 2. And then if we do this in a bigger scale, we can get this barcode, that is a decomposition of features, decomposition of the persistent module into intervals. So this is what we have seen before when we were talking about the Viatori-Rips complex, the filtration, and then calculating the homology, and we saw the different bars. So this decomposition was possible because of this theorem. So that there's a unique way of decomposing this, up to reorderings, of course. So now that we have seen a way to decompose some of them, and we know some variations, we know what these persistent modules are, at the end we want to talk about how we can compare different persistent modules. So if we got a data set and then another data set, can we say something about the similarity of these topological features from these two different data sets? And we can, if we can say this something also in a quantitative way, then it's also like a very good feature. The main tool that is first defined is to compare directly the barcodes. When we see the barcode, we can see that it's actually just a set of intervals. So it's like a multiset. That means that if we get some barcode and some other barcode, they're just a set of intervals. So this is 4 intervals that begin and end in certain points, in certain radius. Then we can just compare this with a matching of these two sets. And the bottleneck distance is precisely this. So this is a matching or like a bijection. And we look at the most distant points resulting in this. So the most the distance which is furthest away defines this distance. So that is why we take the supremum of the overall intervals. So in this case, we can see that x is this, y is this the other. So this is, for example, a specific interval. And then we do a matching of all these possible bijections. And we calculate the bijection or the matching that gives the lowest possible distance. That is the best matching. And that defines the bottleneck distance. And this is a useful concept. And in general, persistent homology is actually useful in practice because this bottleneck distance is stable. And what we mean by stable is that small perturbations in the data set, so in the point cloud, if we have a slight variation in the point cloud, then also this bottleneck distance is only varied in a very small way. There's also a different and lastly a different distance that we can calculate based on the persistent modules themselves and not on the barcode. For this, we construct an interleaving, which is a pair of maps, or maybe a pair of families of maps. I don't know. Let's put this, which go from one persistent module to another. So, for example, a one interleaving would be a map going like this, and then another map going like this, and these have to commute. That means that so this map going to this gives the same subvector space as going from this down here to this, and the other way around too. And also like going from V1 to W2 and going back to V3 should give the same as going up to V3. And also the other way around. So this is an epsilon interleaving. And what the interleaving distance is the infimum or the minimum of those epsilons for which there's an epsilon interleaving. That is, we can of course given an epsilon interleaving, we can, for example, define an epsilon plus 1 interleaving, because given the commutation, so a bigger one always works, but smaller is not the case. Therefore, the interleaving distance is the minimum of those epsilons for which there's an epsilon interleaving. And the nice thing is that these two concepts are actually related. That means that persistent modules, so two persistent modules which have an interleaving distance, if we calculate the barcode of these two persistent modules separately, so for V and for W, then the bottleneck distance of their barcodes is exactly the same. And this interleaving distance can be defined in a more general way, so that's useful. We don't have to go to like barcodes and multisets. We can compare directly these persistent modules. And therefore, we get back to this like general diagram that I showed before, but we got more information. So we again start with data in a point cloud, in a metric space. We calculate the variatory strips complex, and we get a filter complex. We calculate the homology, and we calculate the barcode with. Well, this is just notation to calculate the barcode. We have seen that isometry theorem. That means that the interleaving distance of a persistent module and the bottleneck distance of the barcode is the same. And what is called the RIP stability is that the bottleneck distance is always smaller than what is called the Gromov-Hausdorff distance, which is used to compare metric spaces. I won't go into detail here, but this is the important notion of stability. That means that small changes in the metric space give rise also to small changes in the bottleneck distance. So it's not chaotic or something. The distance describes something which is useful. So
you have about 10 minutes left.
Yeah.
You have a lot of slides, so maybe you want to choose what to skip or not.
Oh no! It's just appendix, so just in case. But I'm just finishing with this slide.
Okay.
So, yeah. So it was like there's like a lot of concepts, but the main things that that can be taken away is that persistent modules are something that started in topological data analysis, but had also found like a categorical language to describe them. And there's actually a branch of like abstract homotopy, which like uses this category theory to branch out a bit. So they're not so much concerned about like data analysis, but about the formal description of these tools. And a lot of theorems and results in persistent homology come from Cuba theory, from commutative algebra, or module theory, for example. And these persistent modules, we can see that they can be decomposed, but it is also important that there's some like weird ones that cannot be decomposed because of some details. But these persistent modules which can be decomposed, they can also be compared in a quantitative way, and we can get information about the similarities between these topological features. And the similarity is not is stable. That means that it doesn't change drastically when we change a little bit of the data, of the starting data. And yeah, I think this has been the talk.